Okay, so we'll get started with most likely our last lecture. We'll see if we can cover one more. This is going to be on monolithic 3D integration of 2D materials. This is pretty heavy on fabrication. Okay, it just takes a lot of effort and resources to make these chips. This is one of the most upcoming topic in the area of microelectronics. Um, Now monolithic 3D integration, as you can see, we have already discussed why 2D materials, right? That 2D materials can give you ultra thin channel, which gives you the best electrostatic gate control, and then even after being ultra thin, they really don't lose out on mobility numbers compared to like silicon, because silicon, when you make it very thin, because of surface roughness scattering, the mobility actually goes down pretty drastically. So we have already highlighted that the future of logic transistor scaling, which is literally to revive the Moore's law, is going to be based on some of the newer materials, and 2D materials is one of the prime candidates, right? Now, if we think about the Moore's law, right, it is probably, even if we make the transistor very small, right? So today we are talking about 7 nanometer node. TSMC have already introduced like 5 nanometer node, and there are some angstrom nodes, but I want to first clear the confusion that these nodes have nothing to do with the transistor channel length. Okay? The transistor channel length today kind of is stagnated around 20 nanometer or so. Okay? It is not scaling. So when they come up with this node, this is a different meaning altogether. We don't really know what is the exact transistor dimension for a TSMC's most advanced 5 nanometer node. Okay? So the limitation of why can't we make the channel much shorter has nothing to do with the fundamental material properties. It has more to do with the lithographic capabilities. Okay? The tools which are made by ASML, right, it's a company based in Netherlands, they make the most UV tools. They cannot currently scale down how small feature we can get using this UV technology. Once that is enabled, these materials are ready to kind of being scaled much further. But then one day we will probably kind of get to a limit where your transistor channel length cannot be made below, let's say, 10 nanometer, right? So what do we do in order to get more transistors? Because Moore's law is nothing but your transistor chip density simply increases every 18 months, right? And that is not happening right now. What is happening is we are just simply putting more and more chips together, and then this is what all the cloud servers are. You're literally having exploding the size of these huge data centers. So the way forward is literally trying to stack now transistors on top of each other, because if I can start building vertically, right? This is precisely why if you go to a city, you will find all the apartment buildings are tall, because you cannot give space to everyone in the lateral dimension, right? So you build skyscrapers. So that's why 3D integration is going to be important for logic transistors scaling and to revive the Moore's law. And to some extent, this has already happened for the memory technology. The flash devices that we spoke about and the flash drive that many of you are carrying right now, do you know how many levels of transistors are there? There are 232 tiers. It's a 232 storied building inside your flash drives. In fact, the most recent one that Micron have introduced has 500 tiers. It is even bigger than Burj Khalifa, right? Burj Khalifa has, I think, around 200 floors, okay? 232, and now it is 500, right? So this is literally building skyscrapers inside the flash drives that you are using. And that has given you this amazing memory storage capability, right? Just 15 years back, all these flash drives used to only hold megabytes of data. Today they can do terabytes, right? How? Because of 3D integration. Okay? So 3D integration has already shown us, what can you do with the storage. It has not been possible for compute, right? So therefore, the size of your memory chips has gone down while the data centers have exploded, right? Because we could not do 3D integration with silicon devices. Why? Right? Why could we do it with memory, but why could not we do it with logic? Because once you have the first tier of devices, because silicon you grow it at a very high temperature, and then you kind of make these devices, right? So, if you want to do another tier of silicon on top, you have to again increase the temperature, right. And if you do that, then all your metal contacts, metal will start diffusing into your dielectric and all sorts of bad things happen. That is why you cannot raise the temperature of your chip, for high end devices, to below above 400 degrees centigrade. So, that is called the back end of the line temperature, which restrict putting high performance silicon devices, okay, in top of silicon devices. This is not true for memory. You can say, okay, memory is also transistors, right, because memory transistors doesn't have to be high performance, because there what does the silicon channel do? It is just for a readout. Remember, memory device, it was a readout, and the storage was mostly in the oxide, the dielectric, right. So, there I do not need really very high quality silicon channel. So, what I could do is, I could simply do some very quick pulse of high temperature, this is called the rapid thermal annealing, and I get a decent quality polycrystalline silicon, not like a single crystal silicon channel which is required for high performance. I could use a polycrystalline silicon, as a channel of a flash memory device, because for memory it is the storage which is important, and for logic it is a performance. Okay, so you need really high quality silicon. Here you do not need really very high quality silicon, right. So, you could build this tri-cappers for memory, while you could not do it for logic. This part is clear, right. So, now the question is, can the 2D materials address this challenge, right, and the answer is yes, because how are we putting 2D material? We grow it on something else and transfer it, right. We make a tier of transistor, we can again transfer, make another tier of transistor. You cannot transfer silicon, right. So, 2D material gives an inherent advantage in stacking transistors in the vertical direction, okay. And then as I told you, there is this problem of your logic unit and the memory unit being separate for neuromorphic computing, because at the end of the day the brain is 3-dimensional. If you really need to have a computing power like brain and make it small, right, you have to start doing 3D, because the brain is actually 3D, correct. When we have this huge gap, remember the size of a data center is like a football field, and our head size is like 6 orders of magnitude smaller. Why? Because it is 3D, the chips are not, right. So, we have to start doing 3D also to address the critical need for artificial intelligence or neuromorphic computing, because of this problem that we had a lot of discussion, right, this neuron synapses and the separation between logic and memory. So, now in this 3D chip, you can dedicate one tier for memory, one tier for logic, and they are right next to each other, correct. So, you can do this kind of a functionality scaling as well, and one tier could be for sensing. So, everything is now compact, just like how your brain works, right. Your different tiers of neurons simply do different functions. That is something you can do with this 3D integration. And this is a slide that you have already seen. So, this can actually mitigate a lot of energy challenges for the next generation of neuromorphic and AI chips. Now, there are different types of 3D integration. Okay, you can do a wafer to wafer bonding. Okay, I will not go too much details into this, because I think none of you are from this area. Okay, there is a chip to wafer bonding and there is a chip to chip bonding. They are just different ways you bond them, and then you use this technology called the through silicon vias. Okay, so you kind of literally take the chip and dig a big hole. Okay, and then you put silicon through silicon, you make these vias, and then you fill it up with metals in order to connect the transistors in 2 different chips. And here is a cross sectional TM. As you can see that these are the vias, which are connecting the different layers of transistors, right. So, this is the silicon interposer technology, which is the holder over here, which holds all the chips, and then they are connected. And this is actually used for this high bandwidth memory. So, not only are they scaling the memory technology in the vertical direction, they are also stacking chips on top of each other. Okay, and that's what is happening with your most advanced GPUs and TPUs. So they use this through silicon via technology. This has been already commercialized. This has already been commercialized. You can do it for DRAM. This is the high bandwidth memory. This is all through silicon vias. Okay. So generally, the key steps of the through silicon via fabrication is that you need to really do this deep reactive ion etching. Okay, which is in order to create this high aspect ratio vias, because these vias are very tiny in the lateral dimension but very long. So, you are trying to literally dig a very deep hole, and that is always is a very big challenge for this through silicon, because you are literally kind of digging it through the entire substrate, right. Just think about digging just a very deep and narrow hole on the ground, very difficult job actually, right. And then you also need to deposit a thin insulator layer on the wall of that, so that when you deposit metal, the metal does not diffuse into other unnecessary parts, right. So, that is the other thing. So, isolate the TSV from silicon, and then you need a barrier layer like titanium or titanium nitride, because the metal, you have to stop the metal diffusion. These are called the diffusion barriers. And copper is most commonly used to fill out these vias because of high conductivity using electroplating techniques, but tungsten and polysilicon are also kind of alternatives. And then you do chemical mechanical polishing to ensure that the TSVs are kind of planarized. So, there is a lot of fabrication process that just goes into just fabricating the via, that we are not even talking about fabricating the chips. Just to connect the chips, you have to go through this extensive process. It's pretty expensive. Okay, so the challenge is that you need precise etching, metal filling, planarization, a lot of processes, and then the TSVs introduce hotspot in densely packed vias, because now certain areas, if a lot of computation is going on, the temperature could be very high, and that could start thermal migration of copper, and that can really mess up with your devices. Okay, so TSVs are kind of good, but they are not the ultimate solution. Okay, there is a new technique which is called the flip chip bonding. Again, I am not going to go into too much of detail of this, because it will not be that interesting for this audience. And there is also 3D heterogeneous packaging, where you just check it, a memory chip, you take a logic chip and put them on an interposer technology or a packaging substrate. So, these are just different types of ways the industry is currently doing 3D packaging, which is also a big thing, and I can tell you that some of you may be interested in 3D packaging, because this is something going to come to India most likely. Okay. So, the interposer right now, this interposer could be literally any substrate. Right now people are thinking about glass. Okay, glass is actually very strong. So, they are using, right now it is silicon substrates, but you can also use glass substrate as an interposer, which is like holding everything together. You see the different dyes. For Indian perspective, the Indian semiconductor mission is currently focusing primarily on 3D packaging. Okay, a lot of companies like Apple, is interested in setting up packaging facilities in India, because we are not manufacturing high-end chip, but you can start putting things together, and that's actually a much more easier challenge, because the labor might be much cheaper in India to do the packaging. So, packaging is actually going to come to India quite a bit. And these are the existing technologies that the industry is currently working on, and there are certain advantages of getting high bandwidth, better thermal management. You can see improved scalability and signal integrity, and also offers high density interconnects. I am just skipping these things, because I mean, once I post this lecture notes, you can go into the details. So, what I want to come to is the fact that this is the trajectory that the industry is currently tracking, 3D heterogeneous integration. And you can already see right now in a given chip, you have like 20 billion transistors, 10 to 20 billion, and TSMC wants to go to 1 trillion transistors. Okay, remember the number of neurons in our brain, right? This is the number that they are eyeing for the most advanced AI chips. This is mostly geared towards AI chips, nothing else, right? And this is going to be very difficult to do with 3D heterogeneous integration. That's why monolithic integration is something that they are more interested in, where you are doing things from the bottom up. Instead of putting things from the top down, why don't you grow it from the bottom up? Okay, that can actually lead to very high transistor density, and this is the TSMC's roadmap actually. They want to jump at some point of time from heterogeneous to monolithic. Okay, and there are a lot of technologies over here. There's a lot of details. You can go and read about each of this topic. That's like a lecture in itself. So, I'm not going to go into that. But the unique advantage of this monolithic integration is that now this via, okay, in spite of making this via very small, there is a limitation. You cannot make this via too small. Okay, you cannot make this via as small as these lines over here. These are the interconnects, because you also have to have interconnects connecting different transistors, and those are actually very tiny lines. And So therefore, you cannot connect a transistor to another transistor. You see, you have to really come through, maybe a circuit can be connected to another circuit, or maybe at the architectural level. So device to device connection is not possible using this through silicon via technology, and that's why it's a bottleneck of getting to this many transistors or circuits or architecture based on these transistors. So what you have to do is you have to start doing this monolithic integration. Then your interconnects can be as small, or your vias could be as small as your interconnects. Okay. So therefore, you can get a better integration density. That's what we are kind of eyeing towards with this monolithic 3D integration. Okay, this part is clear. I mean, kind of an overall view of where this technology is going. Okay, so this is what we have started doing, and this is one of the first demonstration where we actually did a 3D integration of 2D transistors, because so far we were only talking about transistors in one tier. So now this chip has got transistors in 2 tiers stacked on top of each other, with each tier having 30,000 transistors. Okay, so you can see already we published it in Nature because of the fact that nobody has demonstrated this level of integration so far in the field. Okay, people generally report one device most often, maybe 10 device, right? Going and demonstrating 30,000 was a completely different ball game together, right? So we could do it because we have automated measurement capabilities as well. So it's not like a student is going and measuring 10,000 devices, then it will probably take their entire PhD. Okay, and we can make these devices pretty small, 45 nanometer channel length. I have also shown you channels even smaller. We can go down to 20 nanometer channel length, extremely scaled devices, which means that this technology can be scalable. And as I told you, we don't stop at 2 layers. We have like 3 tiers of devices, 1, 2, and 3, right? And therefore, you can now start making all these vertical circuits, right? That's a different domain for circuit designers. So if some of your interest in circuit design, how do you route, where do you place your NMOS, where do you place your PMOS? This has been a problem in the planar dimension. It's going to change completely when you go to the vertical direction, right? So that's an entirely different field that's going to start. Yes.
So I think here mechanical and civil engineers also will have to come in.
Yeah, right? Absolutely. All kind of engineering. You are literally building a skyscraper, but in a chip, right? So whatever engineers you need to build that, you need the same types of engineers to build this chip as well. Yeah.
More than 30,000 device channel length is very huge. So that means that you use, I think,
EBM lithography. EBM lithography.
Like 3 to 4 days to make
this chip, you mean the one tier? The E-beam takes at least 8 hours to write the entire chip. Okay, 8 hours to make the chip one tier, and then another 8 hours for another tier. So there's a lot of lithography steps. I will come to that. That's why E-beam is not the final option. You see, if E-beam was the final option, E-beam can get down to 10 nanometer of channel length. Then TSMC would have been using E-beam lithography. E-beam lithography, the problem is you are going and patterning every device, right? That's not a scalable solution. Ultimate solution has to be optical lithography, or this EUV lithography, right? The extreme UV. Yeah, that's why we cannot have it. That I told you that the ASML tools will cost you 100 to 200 millions of dollars, right? Sometimes even close to $1 billion. So you cannot afford it. Universities cannot afford it. Only industry can afford it. So eventually this will be made using UV technology, right? But we are showing that proof of concept that when you make these devices small, they actually work, and they work according to what is predicted.
And before that, you saw that 3D heterostructure, right? Something.
Yeah.
So there is a thermal management issue.
Yeah, that's what he was saying. Thermal management issue will come in, mechanical stress strain issues will come in. So whatever issues you can think about building a skyscraper will come in this nano skyscraper as well. We have not tackled those issues yet.
And then you did this electroplating to fill the fire, right?
We did not do it. I am saying industry does that, electroplating. Electroplating and mechanical polishing can only be done when it's a 4-inch wafer. It cannot be done on such a small wafer. So we don't do those kind of things. The packaging is something that our group does not work on. But I'm saying is packaging industry is kind of really picking up in India. So this is an interesting area for most of you to consider. And we have other faculties who are doing packaging. So we don't do any packaging of 2D materials. Okay. Correct, correct.
So now what type of software?
We use the same software right now, but it is just very tedious to design these chips. It's not very, yeah, I think we spend probably more time in the design than actually fabricating. because once the design is ready, you just go and write layer by layer. I will come to that, how many layers are there. So this is like some of the devices you see, 10,000 devices measured in tier 1, another 10,000 in tier 2, right? And then these are like scale devices, close to 1,000 for tier 1 and tier 2. These are some cross-sectional TEM, high resolution. And here is the fabrication process. You can see how many steps, right? So first we do this tier 1 gate. First we do the gate, then we transfer, then we do the gate oxide, which is our floating gate. Remember, this is what we want to integrate memory and logic. So we do this alumina, hafnia, alumina. Then we do an etching process, which also will require us to do an E-beam lithography to define the pattern, then go and etch it, right? So an E-beam is involved with the etching. Then we transfer the MOS2. Then we again pattern using E-beam, right? And then we etch the MOS2, right? Then now I have a channel, I have a dielectric, I have a metal electrode. Then I do another E-beam lithography and E-beam evaporation to put the source drain contacts, right? This is how we make tier 1. After that, you put the inter-tier dielectric, because we have to isolate them electrically, right? So that we put something like an aluminum oxide spacer, it's an insulator. So that is my full fabrication of tier 1. Then you simply repeat. Again gate evaporation, again alumina ALD, again gate open, again transfer, again etch, right? Again source drain contact, and then you get to tier 2. And then you keep repeating it, and you get tier 3. And at that point, you have to start etching the inter-tier dielectric and start doing this vias. But these are no longer through silicon vias. And these vias are now very small, and they are connecting transistor to transistor, which we could not do with heterogeneous packaging industry. Make sense? Which gray color? This dark color. This right now we are using, you see the color over there, type platinum. So you can use any other metal. We are not using copper because copper will require electroplating. As I told you, electroplating is more difficult for us to do. So we just use any metal for the interconnect. So there is a lot more engineering remains to be done in order to optimize this structure. This is not a fully optimized structure.
So sir, these are not like,
No? Yeah, there are tiers separating those. These are devices in tier 1, tier 2, and tier 3. This is our N-type MOS device. This is P-type. So we can get the CMOS capability, right? NMOS and PMOS. And then, as I told you, that each of these devices are programmable. So that means I have both logic capability as well as programming capability. So memory and logic both are there. They're all responsive to light. So therefore, they can also be used for sensing. So sensing, logic, compute, all are there in this 30,000 transistors, each of these 30,000 transistors, right? So that gives us enormous capability. And here I write down the number of lithography steps, you see. So if you want to fabricate a 1-tier device, there are 4 E-beam lithography, 1 atomic layer deposition, 2 etching, 1 2D transfer, and 2 metal evaporation, total 10, okay. And then as you go to tier 2 and tier 3, the number simply increases. There are 38 lithography steps. It's a Herculean task for the students who did it. Okay, they I think took not long. They made this entire thing in a month. Okay, working literally day and night. There were 4 students working on this. They were doing this. You have seen this relay marathon, where one person will come and hold the chip. So it was going 24/7. This one chip. Do you know how much did we spend in making this one chip? Just one, that wafer that I showed you, right? You know how much we spend on that? Almost close to $80,000 US. Oh, they just run, they just keep making it. Yeah, continue. So this nature paper costed us close to almost $1 crore.
So what's the via size for this one?
The via size for this one I will come. I will talk about the, you can kind of see already, this is 1 micrometer, you can see the via size from the figure itself. Yeah, via connections. Via connections over here I think was titanium. We use titanium. The via is a metal connecting a transistor in tier 1. You see the contact in tier 2 is getting connected to contact in tier 1. Right, because you are connecting the transistors. literally. So you have to connect the contacts, right? And then this is not where we stopped. Okay, this is the first 1 crore project. Okay, just I mean, I was telling them, the tap is open, and not water, money is flowing when we start making these chips.
All the oxides were deposited by ELT method.
Not all the oxides, the gate oxides are deposited using atomic layer deposition. If we and then the intertier dielectric is done by e-beam evaporation, because that doesn't have to be extremely high quality, because if you do it using ALD, it will just take a long time. So we don't do ALD for the intertier dielectric, we do just e-beam evaporation. Okay, so you can see the number of and every step has to go and work fine, right? Anything goes wrong, you have to start from scratch. So that's why I'm saying, I had to choose the most 4 competent students to do this, and they literally required only 1 try. They did it in once. Okay, so extremely competent students. Okay, but will eventually they were rewarded by this publication in Nature, right? Okay, so next is, we thought about, okay, we have now done, the integration of unipolar transistors, like either N type or P type. Why can't we put them together? So now we started working on tungsten selenide. We did some contact engineering. This is something we have learned in the class. If I use a little bit lower work function metal like nickel, then I can get a N type characteristics. If I use a little bit high work function metal, I get P type characteristics from tungsten selenide. So now I have the same material giving me both N and P. So what we thought about, why don't we integrate this into a 3D architecture where we have NMOS in tier 1 and PMOS in tier 2, right? So now I am making a NAND gate. Earlier this was just simply transistors, now this is circuits and CMOS circuits, right? And you now see what is the via. Via is only 1 micrometer. Very small vias we can make, which is not possible with the heterogeneous packaging technology. Right, here is the cross sectional TM. This is pretty wonderful looking. You see, this is my tier 2 tungsten selenide. Each device has this floating gate stack. Here is tungsten selenide bilayer, and then this is, I think, again tungsten selenide bilayer, right? And you can see the via connecting the 2 tiers of devices. Okay, and then we make all sorts of logic gates, inverter, NOR, NAND, and here is the comparison. Okay. And here you can clearly see that this is where we are competing not with academic institutions anymore. We are literally head on with the industry. And you see what, and these are all through heterogeneous integration, packaging technology. Look at so you should be looking into this number and maybe this number, this via pitch. You see the via pitches of the order of, tens of micrometer. Very recently IMEC, just last year, has introduced one. Okay. And we are just starting in academic institution with this number, right? This is not even generation 0 devices, right? So this is the power of monolithic 3D integration, right? 1 micrometer, in fact, now we have gone down to even 300 nanometer vias, right? So and you can see this is the integration density kind of, right? So number of vias, the number of connections you have per millimeter square, and you can see we are already as good as what is happening with the heterogeneous integration. Which one? BOL compatibility means that we can do it at a very low temperature. The entire process that I showed was done at 180 degrees centigrade. I told you, right, back end there is a process temperature limitation to 450. We are not even close to that. We are at a very low temperature. The thermal budget for making this chip is very low, right? Because the 2D material we are growing on a separate wafer at a higher temperature, and then we are transferring it. So all the lithography processes are very low temperature. Okay, that's another advantage, that we are compatible with the back end of the line. Okay, and then we were talking about just not having more device but more functionalities. This is where we kind of stacked graphene devices on top and MOS2 devices in the bottom. So sensors and compute right next to each other. So we can do something called the in-sensor compute, right? So the previous paper was published in Nature Nanotechnology. The good thing is that we could publish in this Nature sister journal, because this was such a hot topic at then. We have one in Nature Electronics, one in Nature Nanotechnology, and one is going to come out very soon in Nature Communications. So we have literally covered all those higher tier journals using this 3D integration, right? So here again, right? very nice cross sectional TM, and we collaborated with a group of Professor Yang, extremely efficient in getting this wonderful TM image. And I can tell you, this is like the best quality transmission electron microscope images that you can take. Okay, and generally I think TM instruments are even more expensive. Okay, at Penn State we have 6 TMs. Okay, and of them 2 are aberration corrected. We can do cryo TM, amazing facilities. These are all in the building that I showed you, the Millennium Science Building. Okay, and then we have amazing faculty who are equally motivated in collaborating. Okay, so we give them the sample, they give us these TM images within a week. If you go outside to do it, it will at least take you 2 to 3 months. Okay, that also fast paced our progress a little bit. Otherwise, we cannot compete with some of our competitors which are neighbor in India's neighbor. Okay, I guess you can have a guess, which country I'm talking about. Okay. So then we kind of do some experiments showing that we can actually take an analog signal generated by this chemisensor and then digitize it. Because remember, this is something we need to do eventually for any kind of artificial intelligence or neuromorphic computing, right? And now we are doing it in a 3D chip, right? We are not doing it in a separately packaged chip, right? So that's the other advantage of 3D integration. This we published actually as a cover. This is what we were talking about. This was the cover of Nature Electronics. I think in December. I shared it in LinkedIn. It was in December issue or November issue? October issue. Oh, it's already October. Okay, wow. 2 months, 3 months have passed now. 4 months, yeah. Okay. And then you can also do something called the SRAM scaling, because static random access memory, some of you may be knowing about, okay, has 6 transistors. And the main reason that today we cannot really make our GPUs even faster is because the SRAM cell sizes are not going down. But now with 3D integration, you can automatically see the benefits, right? I don't have to put all the 6 transistors in tier 1. 3 can go in tier 1 and 3 can go in tier 2, and then this cell size reduces, right? So that's what we are also trying to do. And this is again, these are all the design software. That's why I was saying the design now becomes way more challenging, right? Because you are not putting 2 transistors on top of each other. There are connections as well, and making this layout design takes a long time. So my students are now getting more pro of using all this design softwares. There are different footprints, there are different ways you can place this transistor. That's why I'm saying it's a new field in itself. How do you put the transistors, where you put the NMOS, where you put the PMOS? So you have to really figure out, how, and as the number of tiers increases, the complexity of the design also increases, correct? So we kind of show that, okay, we can have. So we do it ourselves. We do ourselves, we don't. Yeah, that is where we can, we have in the past done COMSOL simulations. So we will eventually bring in COMSOL simulation to understand the mechanical, robustness of the structure. Yeah. Okay. And this is SRAM array that they built, 3D. This has, you see the area, reduced footprint. These are the, SCM images of a unit cell. This is a cross-sectional TM. Okay. Showing devices on top of each other. Okay. This is another image. This shows that the SRAM cell actually works in this 3D integration pattern. And the advantage is that now you see that in the same technology node, you can have, by even if when you are making a bigger device, you can address the need of a lower technology node, which means that I am able to kind of do better scaling with this 3D integration, which is quite natural, right? Because now every cell will have a smaller area, even if the device dimension remains the same. So generally, you reduce the device dimension to make the cell area smaller, but I don't need to reduce the device dimension. Simply by putting it on top, I reduce the effective footprint, right? That's the another advantage of 3D integration that we are doing. Now, this is our most recent topic. Okay, I hope that nobody else from other places are seeing this video. This is not yet published. So I have told you about, so far we have logic, memory, compute, and this is the ultimate. We are also powering them and making them self-powered, so that you don't even need a battery or anything to run this device. So what are we doing here? We are integrating solar cells in this 3D structure. So that is something that we have started doing. So monolithic integration of silicon photovoltaics with CMOS is challenging. You cannot integrate a silicon CMOS transistor on a silicon photovoltaic, no way, right? The temperature will kill the photovoltaics. But I can do 2D CMOS with silicon photovoltaics, right. So, that is what we are trying to do. So, now the chips are going to be self-sustained. Yeah, the main problem is because silicon CMOS require high temperature processing. At that high temperature, you will destroy the photovoltaic cells. 2D CMOS with 180. That is what I told you, right? The BOL compatibility, right? Very low temperature processing. Silicon you have to put on top. You cannot transfer silicon. 2D I transfer on silicon photovoltaic, right? So why don't we integrate even energy harvesting units with this is the ultimate goal, right? You can do thermoelectric. Yeah, yeah, you can, but you have to read out it. I mean, the easiest source and in the most abundant source is light. True, that's true. That's true. But this is for IoT sensors, right? Resource constrained environment, right? If you want to put it in the external places, right, where you cannot go and change the battery every time. If they are self-sustained, right, and still can give you sense the information and send that information back, will be remarkably completely changing the paradigm, right. So now integrating photovoltaics with this. Yeah, satellite applications, right. This is, I mean, we have a project with NASA and they are actually interested in this kind of things. So that is also driven to some extent by that. So now this is the chip, we have already made it, okay. Silicon photovoltaics in the peripheral, and in the middle we have all the wonderful things. Now the fabrication is even more expensive, right. I mean, first you have to make the silicon photovoltaic, and top of that you are making all this 2D CMOS, right. You see this is the fabrication steps, okay. Lot of materials over there. So this is just one tier, okay. This is the number of e-beam evaporation. So how much did you count? 6, 18, 28 and 35 lithography steps, okay. And then we get to it, right. So these are the silicon photovoltaic. We are using a very simple, not even a PN junction. We are using a Schottky barrier solar cell, platinum, chromium. Because of the work function difference, we get a very nice photo response, and then this is the the design of the 2D CMOS circuit. This is a SEM image, okay. Cross sectional TM again, right, NMOS, PMOS. Earlier I was showing only NMOS and PMOS. Now they are powered by these power rails, which are coming from this silicon photovoltaic, all on the same chip. Make sense, right? And then there is a lot of interesting things going on. So this is going back to very fundamentals, right? It's a very basic solar cell that you can make, because now I have two different metals at the two different contacts. There is a built-in electric field. I don't always need a PN junction, right? And then whenever I shine light on it, right, I can really get this nice photo voltaic effect. As you can see that whenever the voltage is 0, I get a finite current, right. So this is the open circuit voltage and the short circuit current, right, as I keep increasing the intensity of the light. And you do not have to be in solar, even room light. So we were harvesting room light. Yeah, this is not solar, this is very low intensity. Look at the P in, right. I mean, it's like 10 to the power minus watt, minus 1 watt to 10 to the power 1. So 10 milliwatt per centimeter square is literally ambient lighting, right. Even you can harvest that, right. So literally, you put your device under this room light, it works, right. And this is the maximum power. The maximum power right now is very low, okay, 130 picowatts for a single solar cell, right. So therefore I cannot use a single solar cell because my requirement for a 2D CMOS transistor is much higher. It will be of the order of nanowatt. So what do? I go ahead and make an array, right. If I increase the length of the array, then I get much higher open circuit voltage, but I also need current, so I make a lot of them in parallel. So if I create an array, then I get to, you can oversee the open circuit voltage kind of increases, right, as I go to larger series array, and while the current remains kind of pretty much constant. While the current increases, you see this curve which belongs to this side, increase as I get to more number of parallel connections. And eventually I think for this entire array that we have done, which is having a 15 cross 16,000, 1600, okay, that many devices are there, we ultimately get to 2.8 microwatt. With that, I can now, so now my next objective is to make my devices low power, right. If the devices are very high power, then I will not be able to use only this much power to run everything, right. So that is what we do. We actually optimized our MOS2 and WS2 transistors to an extent that now they can work with very low voltages, okay. And then we make all these integrated circuits, layout designs, and we can show that they can operate only with 2 volts. Just with 2 volts, all my logic circuits work, which I can deliver using my, you see what is the open circuit voltage that my circuits can develop? Up to 2 volts, and the currents is up to microamps. So as long as my devices can operate with 2 to 3 volts and requires only microamps of current, I can then run the entire circuits. So these are the circuits which are running on silicon PV powered, right. This is no external power supply, just the logic operation happens with ambient light. Right now it is quite a bit. So I would say that you have seen that what is the size of the array? Yeah, because the efficiency of these cells that we have made, I do not even want to tell it. It is like very shameful for me to tell that number. The number is only close to 0.1 to 0.5. This is the concept, yes. So right now the efficiency of these solar cells are very poor, because you saw what are we using is just a Schottky barrier solar cell. And the solar cell community has really evolved. Today people use perovskite material for getting to 25% efficiency. Our efficiency is right now 100x lower. It is barely getting to 0.2%. So therefore we need a lot of them, right. I mean, this is generally the problem with solar energy harvesting, because the efficiency is low and you generally, that is why the solar panels are so big, right. So therefore in order to run these chips, I need to make so most of the chip, if you go back to this picture, you will see that this device that we are measuring is this tiny, rest are all solar cells. So you can see the ratio of the footprint that I need for the solar cell versus the device. In order to drive even a tiny device, I have need that many solar cells, but we can improve on that. This is right now at a concept, but this is the first time silicon PV has been now integrated with 2D material in a 3D architecture, right. So that is all very brand new, right. I mean, and then we have shown that this operates all the logic circuits functionally, both the combinational logic circuits as well as sequential one, because ultimately if you want to make a microprocessor, so our ultimate goal is to run a microprocessor using silicon PV integrated on chip, right. So we are kind of making progress towards that. Yeah. So I think you have to make sure that the PV part is exposed, right. Wherever the PV part is, it has to be exposed, because then your even ambient lighting can do it.
So if we can, instead of using the solar PV, like I said, the thermal.
Yeah,
so
yeah,
that can be also good.
yeah. You can do that. Yeah, you can integrate any kind of energy harvesting, right. You can do thermoelectric generators as well, right. So lots of work is going on. Yes. Yeah, yeah, yeah. It will be a different set of materials. It's just integration becomes a challenge, because now it will be different sets of material. But in principle, yeah, yeah. It's just much easier because our substrate is silicon. We can simply go and that would be interesting if you can look into that. Yes. Okay, and this just shows that all our logic circuits work, but there is a trade-off, right? The trade-off is that we cannot now operate them very fast, because the power is very limited. I cannot get both low power and high speed. But most of these IoT sensors doesn't require you to measure every nanosecond. If you're just monitoring the environment, do you need to measure the humidity every nanosecond? No. If I measure it every second, good enough, right? That's why I'm telling you guys that the application is important, just not how good you can make your devices, right? So therefore, when you are monitoring, let's say, carbon monoxide in a room, right? Do you need to measure it every millisecond? No, every second is good enough. That will be enough for you to then go and evacuate the building. So the requirement is milliseconds, or maybe tenths of millisecond. Why should I need a device that has to work at nanosecond? No need. So I can then use this kind of devices for this application space, right? This IoT sensing. And then finally, we don't even stop about logic. Then we put another tier, right? Now bring sensing. Graphene sensors are there, right? More fabrication, right? Now you see this is exploding. How much is this now? 7, 22, almost getting up to more than 42 lithography steps, correct? We make it, right? This is the structure. Okay, these are different device structures. This took a semester. This took a semester. Getting all the measurements done and getting the paper ready and stuff. It took us a semester, which is still quite fast. Generally, it will be a PhD. In my group, no. This is just one paper. Yeah, this work is literally a PhD. You can see, right, the amount of work that needs to be done. But that's just one semester's work. Sometimes even only 2 to 3 months. Okay. So if you are thinking of joining my group, then you have to become prepared with the fact that we are literally non-stop. Okay. So and then we kind of do a lot of design, which I can kind of skip, and then we do all those chemisensing experiments, but now on this PV powered chip, right? And these are all complex logic circuits. Let's not go into the details of that. So now we have a sensing module in the top tier. We have a compute module in the bottom, the lower tier, and then we have the silicon photovoltaic from the back side powering the entire chip. Okay, and then we do some very basic things. So you got it, right? So this is a self-powered near sensor compute in a monolithic 3D IC. No, not published yet. Right now under review. Preprint I am not sure. I generally don't put preprint because I do not know somebody gets that idea and then does it, then we will lose it. No. So I generally am not in favor of.
No, sir, like you submitted in like archive and others, if you give, like you submitted in some journal and there somebody can take that idea.
Yeah, no, but I generally, archive is good.
That happened with one of my friends.
Yeah.
By the time it got published,
yeah.
somebody already did and published.
Yeah, because generally publishing in these journals takes a year. I will probably put a preprint maybe like 3 months when I know that this is going to get published, because I do not know whether the paper is going to get rejected, then how long will it take for the revision. So generally I'm not, because these are like brand new ideas. Even if somebody takes this idea and, because archive although it is there, but whoever publishes the paper first gets the credit. You see, I mean, if you have a Nature paper first, nobody cares whether somebody else is an archive paper. Which one will you cite? You will always cite the journal paper because it has been peer reviewed. Archive paper is not peer reviewed. So I'm not a very big fan of archiving. I mean, I put in archive things which are more technical, no problem, even if somebody copies. But brand new ideas, I will hardly put out in archive. Okay. So we were able to do this. And then, these are the remaining challenges that we wanted to solve. This is something we discussed in this review paper. As I told you, if you're interested in 3D, you can read this review paper, very detailed. This is like the chemical mechanical polishing that has to come. We cannot do it now because our chips are too small. You will also need to have this electrostatic decoupling, and your interconnect has to be properly designed. You can think about, somebody was talking about thermal management. Graphene is an extremely good example of a good thermal conductor for spreading the heat, because generally what happens in an integrated chip, a part of the chip is working very hard and that part becomes very hot, and that could degrade the performance. So instead of keeping the heat at that concentrated location, you can use a spreader, because you cannot get rid of it. When it's a 3D structure, it is very impossible for you to get rid of the heat. So you have to engineer it different way. So what we do is, instead of keeping the heat at a localized location where the temperature rises and becomes like 400 degrees centigrade, we just spread it. Right? So graphene is an extremely good example of heat spreader. Even some of the topological insulators like bismuth selenide, bismuth telluride, some of the thermoelectric materials that we use could be used as a heat spreader for thermal management of these 3D ICs. Right? That's an entirely different area of research that's going to emerge pretty soon. It's already going on, but it's going to come up in the next couple of years, right? How do you do thermal management, and what is the materials levels innovation, and what is the design level innovation in order to do the thermal management? And this is what I was talking about, right? How do you engineer these interfacial materials to really distribute the heat? whether laterally, vertically, right. So, a lot of work has to be done over there. So, you can see that there is a lot of opportunities and challenges with this 3D integration. It's a relatively tougher topic to work here, because I feel like you don't have a lot of fabrication capabilities, but you can start looking into some of the design aspects, right. Simulation aspect of these chips can actually be done over here, right. With that, I think this is the end of the 3D integration. If you have any questions,
So
then
all this 2D
I can
material,
take.
like whatever you synthesize, it's like wafer scalable,
Yes,
and it's MOCVD you use?
we are using MOCVD. We are using MOCVD. Wafer scale for us right now is 2-inch wafer. It's not like 8-inch wafer or 12-inch
So
wafer.
what is this that precursor you use, that metal or
So we are using molybdenum hexacarbonyl MOCO6 for the molybdenum precursor. For sulfur, we are using H2S. Uranium, we are using H2SE.
that means everything is optimized, that flow rate, everything is optimized.
We are still optimizing, because we still want to improve the quality of the material. These materials still have a lot of defects. So I am not doing the growth, as I told you. I am not a growth group. So my collaborator, Professor John Redwing and Professor John Robinson's group, are looking into the growth of these 2D materials and trying to optimize it even further. Yeah. I think it will be mouse